In this lecture, we are going to see 0-1 knapsack problem using branch and bound method. What is knapsack problem, and then what is 0-1, and what is branch and bound method, then how to solve the knapsack problem using branch and bound method. Knapsack problem means there are n different objects are given. For each object there is a weight and profit values are given. N different objects, and for each object weights and profit values are given, and also there is a knapsack, or it's also called as a bag with a capacity M. These items are given. An objective function, objective of this problem is filling of knapsack that maximize the total profit earned. So you should fill the bag, but the profit earned is maximum. So the idea behind the knapsack problem objective is maximize the profit earning. At the same time, the filling item, the weights of the capacity should not exceed the M value. This is a problem. When you are selecting the items, what things you have to follow? The sum of weights taken into the knapsack is less than or equal to M. So when you are choosing the items, the item weights must be less than or equal to M. At the same time, you should consider the sum of all values, profit values of the items in the knapsack, filling item, is maximum among all the possible combinations of objects. So this is knapsack problem. Then what is 0-1 knapsack problem? So this is knapsack problem. 0-1 means in knapsack problem we can take fractional item. Suppose the item rice 10 kg available, then we can take 5 kg. Remaining fractional, the portion of the item can be taken. This is called as a knapsack problem. 0-1 knapsack problem means either you can take item or you drop item. So if you want, you take full item or you leave the item. So this is called as 0-1, yes or no, that concept. So the solution for the 0-1 knapsack problem is not variable size, is a fixed tuple size. That means you are going to take whether you take item, if you are taking item, the item 1, not if you drop the item, it is 0. So the solution in that format only. An example, capacity of the M, the capacity of the bag is 15 kg. Suppose the capacity of the knapsack is 15 kg, number of different objects 4, and the corresponding profit values for the 4 items and the corresponding weight for 4 items given. There are 4 items and the corresponding profit values and the weights are given. How to choose, how to achieve the maximum profit? That means you are going to take these items and maximize the profit, but the weight should not exceed 15 kg. What are the ways? Suppose we have chosen, we are going to fill our knapsack by using by first item. You are going to take the first item, second item, you leave the third item, and fourth item you are going to take. So just you are going to leave the third item. What conditions? When you are leaving the third item, how much weight? 2, 4, 9, 15 kg. So first condition okay. And how much profit we can earn? 10 plus 10, 18. 38 we can achieve the profit by filling the 15 kg. And next choice, only we are taking the item, third and fourth item, 15 kg we filled, but what profit we can achieve? Only 30. And when you are taking first 3 items and you are going to leave the fourth item, how much? For example, 6 plus 6, only 12 kg we are going to fill, and profit achieve 32. So among these values, among these possible values, what is the maximum profit we can earn from these items? So the solution for this problem, the maximum profit we can achieve 38. So the item taken into the knapsack are 1101. So this is a maximum profit for this problem. So in this way we need to solve this problem. Branch and bound, the method first in first out, least cost, LC. And this 0-1 knapsack problem can be solved by using greedy method, backtracking, and dynamic programming, and also it is solved by using branch and bound. Branch and bound is is an algorithm design technique which is generally used for solving optimization problems. So branch and bound algorithm optimization problem. 0-1 knapsack problem. Knapsack problem requires maximization, but branch and bound algorithm minimization. So the branch and bound algorithm, in order to apply this branch and bound algorithm, the knapsack problem values converted into the sign, negative sign. Positive values converted to the negative sign. Change the sign and the solution can be changed. So branch and bound and backtracking or state space algorithm. State space algorithm means the solution can be reached by using constructing state space tree. State space tree means the tree constructed to implement branch and bound with a choice for the components is called state space tree. So in the state space tree, root represent the initial state, and at each level the nodes represent the choices made for the corresponding component of the answer solution. So branch and bound is a generalization of the graph search strategy, DFS and BFS. BFS is a first in first out, and DFS is a last in first out strategy. So the bounding functions are used to avoid generating subtrees, like bounding functions at bounding the unnecessarily explore the not necessary nodes, like it avoids the node that does not lead to the answer node. And before and LIFO, first in first out, last in first out. In this method, the selection rule for the next node does not give any preference. Only it gives the first in first out, last out, first out. But in the least cost LC method, preference is given to the node with the best choice to lead the solution. So this is a difference between the before, LIFO, LC, and no difference, any other difference, only this difference only. And this is a mathematical notations for 0-1 definition of 0-1 knapsack problem. Knapsack problem is a maximization problem, but branch and bound is a applicable only for minimization problem. So we convert the sign. So maximize means you have to fill the maximize the profit, at the same time subject to it does not exceed the maximum capacity of the bag. When you are choosing the item, the problem can be modified by the change of the sign. This objective function change the sign for and change the problem. And what is live node, what is E node, what is dead node? Live node means node that has been generated but whose children have not yet been generated. Node only generated but children not explored. But E node is a node currently being explored. That means currently we are expanding the nodes. Dead node is a node that is not to be explored on any further. It's the kill node. This is called dead node. Further we cannot proceed that node. So 0-1 knapsack problem using LC branch and bound tree. This is a state space tree. State space tree is nothing but the tree constructed to implement branch and bound with choice for component selection. For an example, this x11, x10. That means item bag is filled with item 1, x1. You drop the first item. x21 means and x2 item taken, consider, and x2 not taken. So in this way the choices can be made by possible solutions shown by this is state space tree. This branch and bound and backtracking algorithm or state space algorithms. This knapsack problem also solved by using backtracking and dynamic programming methods, greedy method. So this branch and bound and backtracking uses state space tree approach. So this problem, LC start with upper bound and infinitive, and for every node calculate the upper bound value and lower bound value, and in this way explore the nodes. The order in which you are explore the nodes and compare the upper bound value, then which upper bound value is low, that node is explored. This strategy for choosing the next node. This is the difference between the first in first out and LC. The selection rule for the next E node does not give any preference to in the first in first out method, but LC give the preference to the node that has a good chance to getting the searched one answer node quickly. That is the difference. The way you calculate upper bound and lower bound, this is a 1, 2. First initial node, this is a root represent the initial state at each level. In the tree, at each level, each node represent the intermediate selection, that is it corresponds to the choices made for the corresponding component of the solution. So what way we can reach the solution? That choices can be obtained by using intermediate nodes. How to calculate the upper bound, lower bound, the values. For an example, this is a problem given, and there are 4 items. The corresponding profit value for the first item 10, second item 10, 12, and the corresponding weights. Initially the upper bound infinitive for the node 1, for this node. For node 1, upper bound, we are going to fill the bag by first you are taking first item, second item, third item. So profit you earn 32. How much weight you filled? 2 plus 4 plus 6. So totally 12 weights, 32 profit earned. The weight bag filled with 12. What is the lower bound? When you are considering the lower bound, you can take the fraction value. So 10 here. So 10 plus 12, 32. But remaining 3 kg we can fill. 3 kg taken from the fourth item. So profit 18 and 9 kg. So multiplied by 3. So and 10 plus 32, 32 plus 6, 38. So for the first node, lower bound, upper bound, we are not considering the fraction value. This is upper bound and lower bound 38. So since this is a maximize problem, but branch and bound is a minimization problem, you change the sign, minus 32, minus 38. Node 2. This is a node 2. So node 2 means initially we can say upper bound, lower bound we calculated, and node 2 you are taking at first item, and node 3 you are leaving the first item. When you are taking first item, here we calculated the value, so there is no change. First item, second item, third item, so no change. Suppose if you are going to leave the first item, what will happen? If you leave the first item means you are going to leave this item. Then you can fill 10 plus 12, 22. 10 plus 12. So you cannot take this 9 since 4 plus 6, 10, 19. So 15 kg only maximum capacity. So upper bound 22 profit and weight 10, corresponding weight 10. But lower bound you can take the fraction values. So remaining 5 kg fill. So lower bound value 32. So here upper bound minus 22, lower bound minus 32. The two nodes are generated. Which is the next node to generate? The choice made by initially the upper bound infinitive. When the upper bound for the next node, when you calculated that value updated. So now the upper bound is minus 32. Suppose the node, every time you compare with the upper bound value, if it is exceed, you just kill the node. This upper bound is minus 22. It is greater than, so this node does not explode. You can kill the node and you can start with this node. In the same way, you can calculate. You can take the x2 item, you leave an item. You take the x3 item, leave an item. In this stage, when you are taking first item, second item, third item, first item, select second, third item. So your bag is 12. Your bag is 12. You cannot take the fourth item. So 12 remaining only 3. So this is 0, 1 as a problem. We cannot. It's not feasible solution. further we cannot proceed, so here we stop. And here x3 you have not taken, but x4 you have taken, x4 is not taken. In this way you are calculating, and every time you are selecting in the node with the upper bound value, comparing. When you find the lowest upper bound, that updated by the upper bound value. So here upper bound minus 38, so maximum profit we can earn 38 in this. Here this node is not feasible, this is not feasible, so this is a solution. So you are taking first item, second item, not third item, and fourth item. This is a solution space for this problem.